Thank you for tuning into this lesson today. Our topic today is on measures of central tendency, and as an introductory statement, we know that quite often, sometimes when we are in the business, say if you're selling pairs of shoes, you want to find out from your data which is this most frequent shoe size that is bought in a shop. That's very important. You want to find out, for example, the academic performance of one term as you progress to the next term, or you want to find out, for example, the comparison between one class and the other. In all these things, you thinking about the mean, the mode, and the median. And so basically we're saying that a measure of central tendency is a single value that is used to represent the entire set of data, as you can see. Now, and we're just saying that we want to identify, the single value that can best be representative of the entire data. That's what we're saying about a measure of central tendency. Now, the mean, the mode, and the median are basically called average in simple terms, and we have said there are three most commonly used measures of central tendency. And these are the arithmetic mean, the median, and the mode. I will not take time to discuss so much about the objectives and the functions of averages, but generally, as a summarize, averages are used to summarize data. So you condense huge data into a single value, as I said earlier. Averages are also used for comparison purposes. And that averages can also be used for further statistical analysis. If you have the mean, arithmetic mean, you may want to use that mean to get the standard deviation, for example, or the mean deviation. And then we're also saying that averages are also used to trace precise relationship. You want to establish a relationship. Probably the use of regression analysis. We know you can, or your Pearson product moment of correlation, for example, or you can use the average. And then lastly, it is important for decision making. If you are calculating, you have established that one class has performed better than the other one, and the same trainer who is teaching, then you want to find out why is it that this class is having low performance, yet the syllabus coverage is the same, the content is the same, the trainer is the same. So that can be used for decision making. Now, what are qualities of a good average? As I rush again very fast, because this is not really the main thing here. A good average should be rigidly defined. What do I mean? That it should be clear, and there should be only one form of interpretation. So it must have a rigid definition, and rather the interpretation. The next thing that the other quality of a good average is that must be based on all values. You have to include all the values or observations when you're computing a good average. And then we also saying that a good average should not be affected by extreme values. One or two very small or very large values should not unduly affect the value of the average significantly. That's what we mean by that statement. Now, a good average also should be least affected by fluctuations of sampling, or what we call it should have what we call sampling stability. And as I've just explained, that the values obtained from different samples should not differ significantly from each other. That's what we mean. Then a good average should be one that one can easily understand and compute. And lastly, it should be capable of further algebraic treatment. In other words, you can use a good average, an average, to compute another value or variable. For example, we can use the arithmetic mean to calculate the standard deviation, or the mean deviation, or variance. So, then now we come now to the real thing here. We want now to start calculating your arithmetic mean. What is arithmetic mean? Basically, it is found by summing up all the values in a given set of data or an observation varied by the number of those observations. So now, if you have got, say, x1, x2, x3, x3, x4 until xn, how do we get the average? You simply sum up. So you have got x1 up to xn. So the arithmetic mean is given by summing up x1, x2, x3. Sorry, there is a repetition of x2 here, it's supposed to be x3. Then you move all the way to xn. Then how many observations are there in this xn? Xn is the last value of x, and so n will be the number of items in that series. And so we can calculate the arithmetic mean using several ways. The first one is what we call the direct method, and our x bar, or arithmetic mean, will be sum of the values of x divided by the number of x, or divided by n, which is the number of observations. And as we can see our definition here, this is sigma x, summation of x, and n is the number of observations. So for example, you could be asked to calculate the average, find the max, the average arithmetic mean for this max of students. There were 7 students in a class, and they were doing an exam in mathematics. What is the mean score? You simply apply this formula, as we have said. You apply this formula, and as we're saying, we'll add this, then divided by the number. How many are they? There are 7 students. So what we are simply saying is that arithmetic mean will be this sum of x over n. So you sum up those values, and there were 7, so you divide by 7. Then after that, you just get it simple. So it is 122 over 7, which is 17.43 marks. It's just as simple as that. Now, suppose it had frequencies or grouped data. We're going to look at that. But generally, if this is the formula for discrete data, then if it was data that has frequency, then the formula will just change to the summation of f x divided by summation of f. We're going to look at that later, but generally we are saying that instead of summation of x, If it is data that has frequency, then the formula becomes summation of fx. In other words, we are looking at the product of the values of x and the corresponding frequency. You add, then divided by the number of items. This summation of f and n is implying the same thing. It's implying the same thing here. Now, what about the assumed mean method? I want to move very fast. In assumed method, sometimes we also call it the shortcut method, and usually it is used to in cases where you have the data that is being computed is too large, or sometimes you have got values given in fraction. So basically, the assumed mean method simplifies the computation procedure. Now, our assumed mean method, my laptop today is not behaving properly, sorry, but I'm just saying that the assumed mean method is given by arithmetic mean being given by assumed mean plus summation of deviation from assumed mean over n. Deviation from assumed mean. Now, where x is assumed mean, arithmetic mean, am is assumed mean, summation of d is x minus a, deviation from assumed mean, and n stands for the number of items. Now, kindly note that this x minus a may take on values that are not necessarily existing in the data. Sometimes it may be data outside, but the thing that we need to understand is that it will always give you the same result or the same answer. Now, you have an example there, some data on exports for this year, and you want to find out the assumed mean. No, the arithmetic mean rather. You want to get the arithmetic mean, and this data has got several firms, firm 1 up to firm 9, and you've been asked to calculate. How would you go about it? Right, we are calculating the arithmetic mean using the assumed mean method, and from my computation, I have used 62 as the assumed mean, and so based on our calculation, it means that, for example, given the first firm A, if the exports were 12, probably millions, the values have not indicated, this will be 12 minus 62. That's what we mean. To get what? To get negative 50. If I take another value, for example here, let me use 42. It will be 42 minus 62, as you see. Then you will be able to get negative 20. And just like similarly, 92 minus 62. See, if you have 92 there, minus 62, the answer will be 30. So then after you have had the sum of you've had the deviations from the assumed mean, then what you do, you sum them up. So you sum all these values up, and if you sum them up, our value will be negative 90. Now we simply substitute into the formula that we have been given. So our formula was arithmetic mean plus sum of deviation from assumed mean over n. We know that the sum of deviation from assumed mean was negative 90. The number of firms were 9, so it is 62, which is our assumed mean, plus negative 90 over 9, which is negative 10. And if you get that, you get that 52. the question did not give us the units of expression, so probably there could have been dollars or something like that. Now, when we are calculating grouped data, what happens? We are simply saying that this is data that has some frequency of some sort. So it has frequency. You have a value and some corresponding frequency. Now, the formula does not change really significantly, but we're just saying that you can still use the direct method, the assumed mean method, and the step deviation method. Now, using the step deviation method, using the step deviation method, rather using the direct method, of course, as I had earlier explained, because it is frequency, then it becomes summation of fx over summation of f, which is giving you the arithmetic mean. Now, of course, we know that sum of f is the total frequency, and fx is the sum of the product of values of x and the corresponding frequency. So in other words, you multiply f and x, then you get the summation. Just like that. Then you can also use the other method, the assumed mean method, and the arithmetic mean. You know, the assumed mean method and the assumed mean method to calculate. So you have a question there, and I'm sure you can compute this using whichever method you're going to use. But here you have got data, weekly earnings in thousands for 20 workers. It's an airline company. I want you to look at the question. How do we calculate? Again here, because we're using it is grouped data, the values have been so expressed. Remember, this is frequency. Now, if I was using direct method, then I would just get the sum of the product of values of x and the frequency, and then get this, so that your x bar, if you're using the direct method, will simply be 36, 70, just sorry for that, over 20. That's how you get it. But if you're using the assumed mean method, then you can use any of these. And I've said you may use 180 as your assumed mean, you may use 150, you may use 110, 210, 260, or even other values that are outside this given series. Now, in our case here, we have used 180 as our assumed mean, which is our AM. So you are having deviation from the values of x. X 110 minus 180, you get negative 70. Our x is 150 minus 180, you get negative 30. Our x is 260 minus 180, you get 80. Now, we use this to multiply with what? The corresponding frequency. So here, you're using this this column, this column and this column. If you multiply that column and that column, then it brings you to this column. That's what you simply say. So for example, 2 times negative 70 is 140. Then you come here and you get the sum of deviation from the assumed mean. So we know here, for example, here our value is 70. We can move ahead. If our value is 70, then we had used this already. This one we're using the direct method. But if we are using the assumed mean method, then it will be assumed mean plus summation of plus sum of deviation. Sorry, this is assumed mean plus summation of f in brackets deviation from assumed mean. So I'll call it x minus a. X minus a. This is my a divided by summation of f. Now take note that our x minus a is the same as d. So now this is supposed to be our d. Sum of fd over f. So as we're moving forward, our sum of deviation from assumed mean was 70, and so if you divide it by 20, then you get 183. Now take note that this answer is the one that we found earlier, and so the answers are the same. I hope you get time to exercise this, because it is in the exercise of this that we learn, and when we learn, the practice becomes more perfect. Lastly, on computation of the standard deviation, I want us to remind ourselves that in the case of using the step deviation method, we use the assumed mean method. The only thing here is that we divide by a common factor called c to simplify the calculation. So now the formula for step deviation method is given by assumed mean plus summation of f d prime over n times c, where c is the constant that you're going to divide by every term once you have had the deviation from the assumed mean. We're going to look at that later. And that's why we are saying that this d prime is given by x minus a, the sum the values of x minus that assumed mean divided by c, as you can see. Now how do we implement it? Fairly simple. If we are using those values that we are using before, and we want to calculate the frequency has not changed, what we need only to know here is that if our assumed mean is 180, 110 minus 180 is negative 70, and you can do the same until the last value here. Now we want to simplify this data. So how do we simplify? We simply get the deviation from assumed mean, as you see, x minus divided by c. This divided by c is what we are saying is our d. So this is what we are referring to as our d prime. As you can see, is d prime. So it is 70, 30, 70, negative 70, negative 30, 30 and 80. So what is common in these terms? Of course it is 10. So you just divide everything by 10 and you have got those values there. Remember, you have to multiply by f because of this value of frequency. So you're multiplying that deviation, then you're multiplying by the corresponding frequency. Then once you have done that and you have added the summation, you get a negative 7. Now what was the formula? The formula was arithmetic assumed mean plus the product of the deviation from assumed mean and its corresponding frequency divided by that, and then you multiply by that constant. Why are we multiplying by c? Why? It's because here, remember here, we divided by 10 to make the data simple. So when you get the answer, you must multiply it by 10 to go back to the original value. That's why we are saying it is 7 over 20. This is 7. F d prime is 7. Frequency there you have seen is 20. Then divided by that, then times 10. And this answer is the one that we found earlier using the direct method and the assumed mean method. We have an example here again, which I believe that you can take time. These are wages again. Probably let me put them in thousands or in hundreds. Wages in hundreds. So 110 times 100 is, for example, is 11,000. This is 11,200, 11,300. We are multiplying by these zeros. So can you be able to calculate this? You have the frequency there. I'm sure you can get time and you can solve that. Then as I come close to the end of the subject of arithmetic mean, allow me to say that sometimes when you've got continuous data, for example, you have maths students that you want to establish the mean or the median, then what you need to do is to realize that for continuous data, you need to get the midpoint of those values. So in case of continuous series, class intervals and frequencies are given. In this case, we are saying midpoints of various class intervals are kept. So what is the step? Number one, you should get the midpoint and multiply that midpoint by the corresponding frequency. Use the appropriate formula. Get exactly what you had frequency, data, and multiply. That's done. So for example, you have got this kind of data. This is what we're saying is data. Example here, 0 to 10. These are a range of land size. And we know that therefore to get the mean or the median or the midpoint for that matter, 0 plus 10 divided by 2 is 10 plus 20 by 2, 20 plus 30 by 2, 30 plus 40 by 2, 40 plus 20 by 2. To get the midpoint, once you get the midpoint, you can always link it with your corresponding frequency. So that you can write by either method, either you use all the step ratio. I hope you are very hard to understand this lesson. Constant practice as you result. In case you are not satisfied with the presentation, I'm sure you know my contacts. Let's do the same so that to improve the performance of the in our debating institutions. Here